Hi guys, it's Mrs. Allison. Today we are going to begin the last part of this Unit 3, which is our volume. And what we're going to look at today is volume with known cross-sections, volume of solids with known cross-sections. That's going to lead into several different methods, but today we're going to look at just cross-sections. And so what we're going to do first is, as silly as it sounds, is we're going to go over our formulas for areas because these are common shapes that come up in the idea of cross sections. And what we're going to do is we are going to assume each of them has a side length of S. So if we have a square, we know the area is S squared. If we have a rectangle, now this will be a little bit trickier, but if this is my base is S, then we know the area is base times height. Now typically what's going to happen is we are going to need more info for this, and we'll get to what that looks like. A semicircle. Well, a semicircle, if this distance is S, then the radius is S over 2, and we know to find the area, we would do pi r squared. But keep in mind, this is half of a circle, so it's half of pi r squared. And so simplifying this, we would get pi over 8 s squared. Okay, just any old triangle, we know that the area, and again I'm using that base of S, we know the area would be 1/2 base times the height. And again, we're going to need more info on this height. We'll call that H. Now, if it happens to be an isosceles triangle, think what that would look like. If we have an isosceles triangle where both of those are my S, then this area would be 1/2 S squared because it would be, the height would be S. And finally, the equilateral triangle. Now this, to be honest, is a formula most people don't remember. But if all three sides are equal, so this side is S and all three sides are equal, the area here is root 3 over 4 S squared. Root 3 over 4 S squared. Okay, so let's go back to geometry. So we're going to step forward just a little bit from your basic shapes to move into the idea of geometry. And remember, in geometry, and even in some of the lower grades, we looked at how to find volume of a three-dimensional shape. Now, the thing about these three-dimensional shapes, these prisms, or cylinders as the case is in this one, is that if I were to slice it along the entire shape, every slice is the exact same. Okay, so every slice along here is the exact same. So when we talk about finding the area, the volume of these, we know that the way we've done it in the past is we said, okay, our volume for any of these is the area of the base times the height of the object. Okay, so the area of the base, for example, in this rectangular prism, we would take that area and multiply it by the height of the object. The height is what connects the two areas, or the two bases. So in our triangular prism, we would take the area of the prism and multiply it by the height, that distance that connects the two bases. For the cylinder, we would take the area of this circle and multiply it by the height of that cylinder. You get the idea on that volume. Okay, so what works well in geometry, or what worked well for us in geometry, is that the area of the face is the same at every single point within that shape. No matter where I slice it, parallel to the base, every single shape is the exact same. But we know that's not always the case. Such is the case of anything that we deal with, like a loaf of bread, or a watermelon, or a pineapple. If you think about slicing those and you slice them perfectly parallel, every slice is perfectly parallel. Is every size of that piece or that loaf of bread the exact same? No, we know it's a little bit smaller as we move towards the ends, moves towards the heels of the bread. Okay, same with the watermelon. In the center, they're nice, perfect triangle shapes. They get great. But then as we move further out, the shape of it changes, right? We don't have those same nice triangular slices. And same with a pineapple. While some of them may be perfectly round, that nice cylinder shape, the cylinder continues to shrink or grow depending on where you are in slicing the pineapple. Okay, so let's think about this mathematically. And I'm going to scroll up again. And we are going to imagine that we are slicing a loaf of bread. Okay? And when we're slicing the loaf of bread, we run a knife through it. We create this shape. And if I could slice it as thin as possible, almost two-dimensional, right? If we slice it along there and we look at the shape of that, we have an area that can be calculated using calculus. Okay? So we know then that to find the volume of this shape, if I want to take the volume of a single slice, what we're going to do is we're going to make the thickness, instead of it being this two-dimensional piece, we're going to make it three-dimensional. We're going to make this thickness, if I'm slicing it perpendicular to the x-axis, we're going to make the thickness of this piece of bread dx, or delta x. Okay, so we would say that the volume of a single slice is the area of the slice multiplied by delta x. Or maybe we look at it like this. And if I want to find the sum of all the slices, meaning I want to find this volume, what I'm going to do is I'm going to add up each of these slices. Imagine cutting them infinitely smaller and smaller. Okay? Kind of like the Riemann sums, right? If we continue to take infinitely small slices of this bread and we find the volume, infinitely small widths of the bread, that's that dx, and we go to find the volume of this, we would find the volume by taking the sum, which is the integral, from A to B of the area of one slice multiplied by the width. The area of the base multiplied by the height, or the width in this case, of the shape. We're using geometry formulas. Now what we're doing is we're putting them in terms of calculus to get us what we want. So we know that finding the volume of a shape can be found by taking the sum from A to B of all of the slices, the area of the base multiplied by that width, that height of the shape, that infinitely small distance of delta x. Now there are several methods we're going to work on for the next really 3 days. So we have something called the disc method, the washer method, the cross-section method, which is what we're working on today, and then the shell method. We're going to look at each of them in turn, but we're going to start with what's called a known cross-section. Okay, so how many of you, and obviously this is rhetorical, have been in either Mr. Allison's class, maybe Miss Story's class, where you've utilized the 3D printers? Okay, so I want you to picture a 3D printer for me. And what happens? The print head goes along and it builds from the base. It always starts with the foundation of the base. And then it runs the print head along until it builds your shape up from the base. Okay, can you envision that? Or have you used a 3D printer or know what it looks like? If you haven't used one, ask me and I'll gladly show you the one that we have, so you can see some ideas of what a 3D printer does. Okay, so I want you to picture that. The shape that's going to be our base is going to be the shape on the XY plane. So however it's defined. Typically, we're going to define it with equations, and we're going to look at an example here in just a second. Typically, we define it with equations. That's going to be our base. Now, what we're going to do, this base is the solid on the XY plane. What you're going to be given is a cross-section, meaning it's going to say, hey, if you take a really thin slice of this shape, the thin slice of that shape is going to have a shape of its own that we're going to take. Okay, we'll look at an example here in just a second. And you're going to need to find the volume of it by taking infinitely small shapes and adding them all up together to find the volume. Okay, now you can take these with perpendicular to the x-axis, so with respect to x, or you can take them perpendicular to the y-axis or with respect to y. So it really depends on how the problem is laid out. Most of the time I will say that you will see them perpendicular to the x-axis. All the ones we're going to look at for a little bit, I think are. We may look at one that's not. Okay, so I want to show you visually what this looks like. Okay, so I couldn't find a way to embed the GeoGebra link that's right here into the web, into this presentation. So I created a screen recording. It's obviously not quite as good. So if you get a chance, go try this GeoGebra. It showed part of it. It just didn't show the animation. So watch this. Okay, so I want to show you what that GeoGebra site looks like. I tried to embed it in the video and that didn't work. So we're going to try it this way. So this is the same shape that you have on your notes. And what I hope you can visualize is what is going on over here. We're going to just move this purple line just a little bit so we can see it a little bit better. Okay, so if we have a known cross-section, let's say our known cross-section, meaning our slice that we see is a square. So what it visualizes in 3 dimensions is the base of the XY plane that's created by the two shapes does now have a square raised up from it. And if we start adding in different amounts of squares, you can see how it creates a solid shape that we can find the volume of. Okay, so the more squares, the more infinitely small width the square is, the more accurate that volume is going to be. Okay, now our cross section could be an equilateral triangle, in which case what's coming up from the base of the shape is an equilateral triangle, and as we add more we get a different solid shape. And again, we could do semicircles. So you can see that as we play with this, and I can move this bigger and further and we can have it touch the whole shape. But you can see how that base of the shape is that perpendicular line to the x-axis in this case. So everything we'll be doing here will be with respect to x in a problem that looks like this. Okay, so that is what that GeoGebra site looks like. Oh, shoot, I wanted that to move away too. Let me move it up. Okay, so when we talk about volume of known cross-sections, if the cross-section is going to be perpendicular to the x-axis, say we have a shape very similar to what is above, right? So we have this shape in the xy plane where we have one function here, we'll call this g of x, and we'll call this f of x. It makes sense that our cross-section, our rectangular tiny little width right here, is perpendicular to the x-axis, and this distance right here, remember that infinitely small width is dx. So the volume for this is going to go from A to B, A being the low bound, the lowest bound that we have here, to B, the highest bound that we want to find the volume of. And we're going to do A of x, which is the area of the shape. Okay, so we have a side that we're going to deal with, which is going to be our top minus our bottom. That's going to be the side of our shape. And therefore, when we go to find that, it'll depend on what our cross section is to be able to determine the area of the base. So remember, we're going to use then to find the area, we're going to use the side length and then the formulas above. You know, those geometry or earlier area formulas. Now, if the cross section is perpendicular to the y-axis, so maybe we have, I don't know, we'll call that f of x, and then we'll call this, let's do something like that, g of x. It might make more sense on this one to do it perpendicular to the y-axis. So this width, infinitely small width, would be dy. And when I go to find the side of my area, or sorry, side of my shape, the side of my shape this time is going to be the right function minus the left function. And then the area, again, we're going to use our formulas. Okay, let's look at some examples. So let's look at this first example. It says, find the volume of the solid whose base is a triangle bound by y equals negative 2x plus 2, x equals 0, and y equals 0. So if we can picture the base of this shape, and maybe if it helps you, the base of my shape is this triangle right here. So this is going to be the bed of my 3D printer, what's on the 3D printer. Now what's coming up from it says the cross sections are squares. So picture this when we, just so you know, I'm terrible at drawing at 3D, but if we have a square here, if we have the base right here of this infinitely small square, we have some shape coming up three-dimensionally. Goodness gracious, that looks like a square. Mine does not, but it should look like a square. Who are perpendicular to the x-axis. So that tells me the fact that it's perpendicular to the x-axis, that this is going to be dx. Okay, so I want you to think about the side of the square. Okay, and maybe if you redraw the square so you can visualize what it actually looks like. And we know that this distance right here, that side, is the side that's on the printer bed or the XY plane. Now, if we think about the side of this, I know this dimension right here starts at the equation negative 2x plus 2, and then I take away 0 because of the x-axis. And so my side length here, if we think about our side length, we'll call this S. S is negative 2x plus 2. Now, when we talk about the area of this particular shape, we know the area of a square is base times height, but the base and the height are the same, so we know the area is s squared. So we know this area is negative 2x plus 2 squared, or it might be easier to think about it in its FOILed form, 4x squared minus 8x plus 4. Okay, so that's just the area of the square. Now, when I go to do the volume of this, I know to calculate the volume, I'm going to calculate the bounds are from 0 to 1 of the area of the shape, which we said was 4x squared minus 8x plus 4, times the infinitely small width of each rectangle. Because I need to find the volume, and we know volume is area of the base, which is the square, so the area of the square, times the height or the depth of the square, and the depth of the square in this case is dx. So if I want to find the volume now, I'm just taking the antiderivative. So my volume is 4x cubed over 3 minus 4x squared plus 4x, and I'm evaluating it from 0 to 1. The 0 is nice, it cancels everything out. So I would have 4/3 minus 4 plus 4. So I know the volume of this shape is 4/3. Okay, questions on that? All right, let's move on. The next thing says to set up, but not to integrate, the integrals for the volume of the solids with the same base as in example 1, but whose cross sections are semicircles perpendicular to the x-axis. Okay, so we have this same shape, and I'll draw it in a different color, but now the cross sections are these semicircles that the diameter of the semicircle is connecting or is touching the entire base. So let's think about the side for this. Well, the side for this that we need is still that dimension of the circle, the semicircle, is still this dimension here, right? And it's still negative 2x plus 2 minus 0. So the side actually doesn't change. We knew that. But remember, this represents the diameter, not the radius. And remember, to find the area, we know the area of a circle is pi r squared. Oops. My goodness, that's not what it's supposed to say. Pi r squared. But I am taking half of the circle, so a semicircle. So my area would be pi over 2 r squared. Well, I need to figure out what r is. And if I know the diameter, can I figure out r? Well, of course. R is going to be negative 2x plus 2 divided by 2, which means it's going to be negative x plus 1. So let's go and think about my area. My area is going to be pi over 2 times r squared, so times negative x plus 1 squared. Now, if I wanted to find the volume, because remember it says to set up an integral, my bounds of integration haven't changed. They're still from 0 to 1. And then I'm going to do the volume of a of x, which is pi over 2 times negative x plus 1 squared dx. So this would be the volume formula that I would try to find for a solid that has a cross section that's a semicircle. So when it's 3D printed, in the end, you'd see just tiny slices of semicircle all the way through. Okay, let's look at another one. All right, so let's look at this one. This says set up and integrate, so we're doing both, an integral for the volume of a solid whose base is bounded by y equals negative x squared plus 2 and y equals x, and whose cross sections are rectangles of height 1/4 that are perpendicular to the x-axis. So what I would like you to do is hit pause, and I would like you to I would like you to sketch a graph of the base of this region. What does it look like? What does my xy plane look like? Where are these rectangles coming up from? All right, hopefully you had a chance to sketch that graph. And if we look at a graph of this, y equals negative x squared plus 2 is a parabola whose height is 2 max. One, two, three, four. Okay, so the parabola looks like this. And then the line y equals x Looks like this. So you can see the base of the shaded region. That shaded region would be just in here. And that is the bed. That is what the shapes are going to come up from. In this case, one shape. So it says our cross sections are rectangles, and the height of them is only 1/4. So we've got this tiny little rectangle in here whose height's only 1/4 high. So let's talk about the side of this rectangle. Well, we are going to integrate with respect to x because it said it's perpendicular to the x-axis. So remember, our side length of this rectangle, if we picture this rectangle here, this is the part that's on the shape, the shaded region, and we know the height is 1/4, so keep that in mind. But I want to find this side length. And we know the side needs to be the top minus the bottom. So this side here would be negative x squared plus 2 minus x. Okay? And the area, because it's a rectangle, is the base. Well, the base is the side, so it would be negative x squared plus 2 minus x times the height, which is 1/4. Because remember, that's what it said. And that's my area formula. Now for the volume, when I go to write the volume, I would take the sum of all the rectangles who have an area of 1/4 of negative x squared minus x plus 2. I needed it to be in descending degree order dx. So there's my volume, except what am I missing? I am missing the points of intersection, and I didn't draw mine very clearly, but I'm missing the points of intersection. Now, if you could see them from the graph, great. If you're not comfortable seeing them from the graph, set negative x squared plus 2 equal to x and see if you can't find them that way. So we would get 0 equals x squared plus x minus 2. So we'd get x minus 1, x plus 2, which means we get x equals 1 and negative 2. So my bounds of integration are going to go from negative 2 to 1. So here's the integral. I've set this up. Now I need to actually integrate it. So hit pause, see if you can get the integral of this, which is the volume of those shapes, and come back and check your work. All right. If I integrate this, I'm probably going to pull out the 1/4. Just because I think it will make it easier for me. So I get negative x cubed over 3 minus x squared over 2. Oh, good, we get fractions. Plus 2x evaluated from negative 2 to 1. So if I plug in 1, I would get negative 1/3 minus 1/2 plus 2 minus, if I plug in negative 2, I'd get negative 8 over 3, which would be positive 8 over 3, minus 4 over 2, I'll just put minus 2, minus 4. Okay, so combining my fractions, I get 1/4 of, negative 1/3, so negative 2/6 minus 3/6 would be negative 5/6 plus 2 is going to give me positive 7/6. 8/3 minus 6. 8 minus 18 would be negative 10 over 3. And so we get 1/4 of 27/6, or 27 over 24. Okay, so that is how we find the volume of a solid who, if we slice it anywhere along that perpendicular to the x-axis, the cross-section would be a rectangle. All right, let's try another one. Okay, these next two actually go together. So I would like you to hit pause and try to see if you can set this up in any way. Okay, I threw you for a loop on this one because this is perpendicular to the y-axis, and I gave you this circle equation. And if I want to find the volume of the solid, I need two equations that are happening in here. So the first thing I'm actually going to do to be able to figure out my equations is I'm going to take this x squared plus y squared equals 1, and I'm going to get x by itself. So I'm going to put it with respect to y because it said it was perpendicular to the y-axis. So solving this, I would get x equals, that would be 1 minus y squared, and then it would be plus or minus the square root of 1 minus y squared. Looking at that, x equals plus or minus the square root of 1 minus y squared, I would have a positive 1 minus y squared here and a negative 1 minus y squared here. Okay, so if my cross sections, says set up the integral for the volume of the solids whose base circle and whose cross sections are equilateral triangles perpendicular to the y-axis, it means that my base is right here, and it's an equilateral triangle, meaning all sides are equal, that stands up from that shape. Okay, so it's kind of a three-dimensional look, if you will, when we look at it like that, right? So it's these triangles that are standing up from this. So the first thing I need to think about is this side of the triangle. So if I have this equilateral triangle where all my sides are the same, and this is the side that is on the shape, I know my side is going to be the positive square root of 1 minus y squared minus the negative square root of 1 minus y squared, which means my side is 2 times root 1 minus y squared. And remember, we said the area for an equilateral triangle is the square root of 3 over 4s squared. So the area for this would be root 3 over 4s squared, which would be 2 root 1 minus y squared squared. So simplifying this, we would get root 3 over 4 times 4 times 1 minus y squared. So we'd get root 3 times 1 minus y squared would be my area. Oops, I put a of x. I meant a of y. Okay, so now let's write an expression for the volume. Since it's with respect to y, I know I need to use dy as my infinitely small width for the shape, but what about my bounds of integration? Well, I'm on the y-axis, so I need to go from this y to this y. So my bounds of integration are going to be from -1 to 1. And since the question just asked me to set this up, we are done. Okay, I would like you to try the last one. See if you can get it. So hit pause and come back. All right, last example. So this time we are creating rectangles whose heights are 3 times their bases. So I have this rectangle, if this is the base of my rectangle, that's sticking way up here, right? We can visualize it being 3 times, and that's probably not even 3 times. So let's think about the side of my shape. And I'm such a visual person, so I always draw it. And my side is the dimension that is on the base of the XY plane, or the base of the 3D printer, if you want to picture it that way. Well, guess what? Whether I'm using a rectangle, a circle, a triangle, it doesn't even matter. The side is still the same as the one up above, right? The side is still going to be the positive square root of 1 minus y squared minus the negative square root of 1 minus y squared. So the side is still that 2 root 1 minus y squared. Side didn't change, but the area sure will, because we're doing the area of a rectangle whose height is 3 times the side. So when I go to find my area formula, and remember it's with respect to y, my base or my side length is 2 root 1 minus y squared times 3 times 2 root 1 minus y squared. 3 times the base. Okay, so combining these, we would get the area of y is, looks like we've got 2 times 3 times 2, which is 12, and root 1 minus y squared times root 1 minus y squared. So we'll put 12 times 1 minus y squared. And now my bounds haven't changed. My bounds are still the same as what they were before. So when I go to find the volume with respect to y, my volume is going to go from -1 to 1 of the area of the shape, or the area of each slice, multiplied by that tiny infinitesimally small width of dy. And since it just said set up, we are done. Okay, so your assignment is in Canvas. It is a worksheet, and that will be due back in Canvas. And we will see you tomorrow.